in a thick submanifold with boundary. Whenever I say manifold with boundary, I mean manifold with cornea, so the manifold with boundary which is locally smooth and some cornea. So let me just recall, we start with a reminder. We had a long weekend, so before that there is we start with a locally symmetric manifold. And we want to somehow estimate the topology of it all the time. So first we're going to throw out some submanifold, which is singular, which consists of short view that is will expand. But actually in the non-uniform arithmetic case, we're not going to do that. We will not be able to do that. But then we will define. We will show that actually I gave you already the lemma of how to do a deformation retract, and we will deform what's left to the thick part of the manifold. And then we are left with the thick part. This is the thick part. And the thick part is, unlike the picture, is connected actually. And the thick part so sometimes we won't take all the thick part by the submanifold of it, but it will always be of the form or the universal cover of it. Remember that if I did not set by a letter, then when I do tilde, I mean the equation is the universal cover. So it's the complement of the set X. So X is the thin part, if you want, and X is of the form the union of gamma in gamma minus 1, and sometimes I'm not taking all the elements of where the displacement function is less than epsilon. This would be the Margulis constant or something similar to the Margulis constant. But sometimes I don't take all the elements. Sometimes I would like to take, so let's write gamma prime. So this is a subset of gamma, which I would like to be invariant under multiplication, but it could be, for instance, a set for unipotent gamma or something. I don't need, not always take all the. So you see, and this is a locally finite unions. Of nice convex sets. So of convex sets with smooth boundary. So think between this is the, I call this set xi, say, so this is the something like this. So it consists of convex sets with a smooth boundary, and okay. The problem again that it could have some very sharp points, like you could imagine something convex like this, and outside is set where we have large inflexivity radius, but when I put a ball here and intersect it and look at what's left, then it's not contractible anymore, and I want to work with contractible sets. Actually, the optimal was to work with convex sets. So then that's why we will take a neighborhood. We'll take okay, so this will not be so too many sets here, but the point is that this and then this, and then I will take a I will shrink the complement. And when you take a neighborhood, so you make it better, and then you will not have sharp point anymore. But still, I want to construct a simplicial complex here using balls. And the problem that balls are not convex anymore. And still you want to contract to the center of the ball, but suppose the center of the ball is exactly on the boundary. So you cannot contract to the center. So the solution of that is that we will take another smaller neighborhood. So we will take another smaller neighborhood, like this. So maybe I'll use a different color. So take another smaller neighborhood, which is very small. We will have to move somehow that we don't change the homotopy type. We will do that, and then we will take the centers of the balls outside the blue set. So I will take balls, intersect them with the shrinking of the thick part, and I will take the centers outside the blue sets. And I will use balls whose centers are here, and then I claim that in that case I can always, the sets will be contractible. I can always contract to the center of a set. So if I have intersection of set, there will be a point here to where I can contract. So that's what I'm going to do. And this will be the good cover that. So this is what I'm going to write explicitly here. Let me just say that, okay, we are using here the star shape contraction. So let me just say something about star shape contraction that I'm not going to use this talk, but last time I said something not precise, so let me just correct it. So let A be a convex set, and X, a point in the boundary of A. So let's A be a closed convex set. So if A has empty interior, or any point in it, okay? So at the point, a unitangent vector is supporting S, supporting A, if the geodesic ray is C from 0 infinity to S, which satisfies C of 0 equals X and C dot 0 equals N, projects to X on A. So it means that this is X, this is A, this is the point X, and I want, in that case, it's orthogonal, so it's something that the nearest one projection. So you want the projection on A of this all geodesic. You want it to be just like this. Then it supports A. Okay, so at any point, at any boundary point, there is a supporting vector. This you can deduce from the Coulomb theorem. They cannot all. It's the exercise. But so if you want U1 of A inside the tangent bundle T of S, be the supporting vector, supporting a unit vector, and okay. Now, if B is a set containing A, if B contains A, we say that B is nicely star shape with respect to A if the function from let's call it L, the length function from U1 of A to R plus, which give at any direction, so this is B, it will give me the length that I can go inside. So it will be, and direction it will be the length, notice the length of, let's call this geodesic we can call C and H. Depend on the geodesic. So it gives me, so to a supporting vector, it gives the length of C and H of R greater than 0 intersection with B. How much time it stayed inside B. So you want this to be continuous. It's like if this function is continuous. So you don't want that in B there is sometimes there is some jump like this. You don't want, okay, then B is nice and star shape, and then the lemma, it's easy and then it's easy to actually, the lemma, the following, so if A in S is convex and B1 contains A and contained in B2 are nicely star shaped with respect to A, then there is a contraction from B1 to then there is a contraction from B2 to B1 and from if you want S minus B1 to S minus B2 I should say interior of B2 or to keep the boundary. Okay, that's and this is completely easy. Like what you do, you have A, you have this is the first star shape B1. A, here you have second star B2, and you just flow. You look at the nearest point projection, it just flow in this direction, or you flow in the other direction. And okay, it's a very easy lemma. We don't really have to use it because we had this lemma 3.2, which told us how to very general way to define the formation retract, and we can always use that. But in the rank 1 case, maybe I'll discuss it tomorrow, maybe the day after. I want to be a very short proof of everything in the rank 1 case, and then you can use this rank 1. Okay, now let me come back to, I deleted this, but maybe you remember the picture, and what is the general lemma, how to construct intuition complex. So, still I want to call it lemma with the name. I call it lemma 4.1. So let M be local symmetric manifold. Epsilon be some constant, maybe the Mogul constant, maybe it will be smaller than the Mogul constant, and M prime is a connected submanifold with boundary, which is contained in the thick part. Now, I want to construct a simplicial to list some assumption that will allow me to construct a simplicial complex. So first I want some constant. Okay, I will do it. So, okay. So write again x be m, the complement of m prime before, and assume that suppose that x, the universal cover, is a locally finite union, of convex set with smooth pattern. Then okay, this is important. Suppose there exists a constant b bigger than 1. So if you remember, we had this function beta. B will be is something like 1 over beta. So beta was a function, but b will be a constant. But okay, you will see. Such that for every x which is so for every x which is in an s minus x tilde, and the distance to x tilde is less than epsilon, okay, let me write this union is over the set I. So union over set I of this I. So every such x and every I in I such that the distance from x to the convex set is I is exactly the distance of x to x tilde. There is a tangent vector, unit vector. So it's very similar to the condition we had in this deformation retract lemma. So this will be the same such that the inner product with the gradient of the distance function xi at x is at least 1 over. Okay, I have to explain this condition. Somehow I want to control the angle between this between the sets. So I have the sets xi, x1, and then x2, and I have a point x which is not large, which is not far from the. So I want to say that at any such point there is a direction which is in a good, so in this case I only need to consider the set of smallest distance. So in this case, this will be the direction. In this case, where the distance is equal, I have to find a direction which has large inner product both with the gradient of the displacement of the distance from this set and both from the distance from that. So I want a direction that will that will get me farther from here and from here at some speed, not too slow. So this, in a sense, it's telling me that the angle here is not too sharp. Because if this was x1 and this was x2, then here I will not know what to do. Like, okay, in this case you can say we go in this direction. If it was even smaller, you need it in some constant speed. So this is something you need. Okay, now I also want to assume also that M prime is homotopic. This notation I use for homotopic to its epsilon over 2 shrinking. Remember what is shrinking? Should I redefine? Yeah. So if I have so first I define this for general thing. This is just the neighborhood, the tau neighborhood. So it's a union of both of values tau over all x things. And if M prime is the complement of x, M minus x, then the shrinking is the same as the complement of the neighborhood. It just so I want it to be homotopic. So to prove it homotopic again, we will use this lemma of the formation retract, the formation retract lemma.
So tau is the radius of the ball.
Sorry?
Tau is the radius of
Tau is the line. I always use different notations. Maybe I should write x tau. I don't know. I always use when I write a ball around the center and with the radius, I always use different notation. But yeah. Okay. And actually, this is all the condition. This is all the condition I mean. Then M prime is homotopic to P alpha volume M prime, simplicial complex, where D and alpha depends on where D and alpha depends on small s, epsilon, and the constant. But when we will apply this lemma, we start with S, and then we will know what is F. We will define epsilon and B. And okay, so now I want to prove this lemma. So it's a important lemma. So yeah, it's important lemma. It's one of the important steps on this work. So here is the proof. So there are several steps. So step one. Step one. So we remember what is the idea. The idea, as I tried to tell a few minutes ago, is first I take this epsilon over 2. I would like to take the epsilon over 2 neighborhood. And then I will take another small neighborhood. And I would like to cover, to take a cover with centers outside here. So I need to estimate the distance between these two things, because I want the center to be here and I want to use not so large balls. So I need to estimate the distance. So the first thing is that for any tau and delta positive such that, let's say, tau plus delta is less than epsilon, another assumption, no, we have that M tau plus delta. And then I take the B delta neighborhood of it. This will contain the shrinking by just tau. So I need this tau and delta because then this will be tau and this will be delta. And okay, this is the complement of m prime is here. So this is tau and this is delta, and at the end tau will be epsilon over 2 and delta will be something. But this is what I need. So in other words, what do we need to say? So this is equivalent. So this is the lemma. So the lemma is equivalent to saying that if I look at the complement, so the complement of m prime is x, and I look at its tau in delta neighborhood, this will be contained in the x tau okay, let me say what?
You take the tau plus delta neighborhood and then shrink by delta, right? Or shrink by b delta. That should be contained in.
Let me write it the following. I want to say that for any point here, for any point which is in the shrinking, I can find a point, or for any point. What I want to for? It's just confusing. I need to bring this. What we need to show is that we need to show that for any point x which is in the m prime tau minus m prime tau plus delta, there is y which is not in x tau plus delta. Oh, so for any x m for any. I'm confusing myself here. It shouldn't be. So for any x which is in m prime tau minus m prime tau plus delta, which is the same as x tau plus delta minus x tau, there is y in x tau plus delta with the distance from x to y is mostly delta. Okay, this is just a bit confusing, but okay. So how you show that? So let me just draw the picture and explain the idea. So this is x, if you want. This is x. And this is x tau. This is the tau neighborhood of x. And you take, and now you want to take a point which is a point x which is in the tau plus delta neighborhood, so a point which is in the, this is x tau plus delta, and you want to show that you can find this is the point x, and you can find a point y here which is not too far. And the reason is that you can draw actually a line between them. So what will be the line? So at any step you just start to flow. So you are in some point.
I think that's why is in tau, right?
Sorry?
Y is in x tau.
Yes, tau.
Y is in x tau plus delta. So x, so actually, so for any point here. So
But then you can take
here
y
was
equal-
here. X was here, right? X is in
Why should be x tau, not tau plus x?
what?
X should be above the tau neighborhood for sure.
X is above the tau neighborhood. Yeah.
Because
X is somewhere here.
somewhere there. Yeah, that's
Why
right.
should be
You need to find a y in.
Y here.
Yeah, y
Y.
somewhere there.
Yeah, so this is X and this is Y. So I need to tell you how to find this Y. So Y will be the end of some line. I will go on. I will tell you a path on which you go for B times delta times.
But you want y in x tau plus delta is
So Y is in
outside tau plus delta. Inside
Y should be what?
x tau plus delta neighborhood of x.
X is this.
That also seems to be.
Yeah.
Yes.
What? Y will be.
Y should be inside. No?
Yeah.
Yeah. Okay.
Below,
Y should be-
below
Y should
there,
be-
somewhere.
Yeah.
That also.
Yeah.
Yeah, because it's equal to delta.
Yeah.
Doesn't equal to b.
Yeah. Okay. So the reason, so I just need to tell you where to flow, in which direction. And the idea is that at any, so you are at point X, and suppose I'm starting to inflate. I have this tau neighborhood of X, and I start inflating it at constant speed, like with the time. So it inflates exactly at the time, and then this point X will escape farther, so it will never be inside. So I just need to tell you in which direction it will escape. So it will escape in the direction that is given by nx. But the speed that it will escape is b times the time. So it escapes b faster. So this condition tells you that
That's what the.
this condition tells you that it will never enter. So if I'm outside, so I have a balloon here and a balloon here, and I'm inflating them at constant speed. And I have a point which is outside the unit of this balloon, and it escapes at b times the constant speed, and it always has the direction to escape. So it will escape, and after b delta second, it will be still outside the balloon, but then the balloon will cover off. Yeah, so this is the intuition of the proof. So okay, my paper I wrote did the proof of, but this is exactly the intuition. I don't want to write explicitly, but I think it follows from the fact that I have this direction. At any point I have this direction, so it's if you go in this direction of times of speed b, you increase the distance from each of the xi by at least one, or at least the time that you do. So that's in that interval. Okay, so this is good. Why do we need this? So what it follows. So let me just tell you. So this was the only lemma that I don't need this tau actually. Tau will be epsilon over 2. Tau will be epsilon over 2. And the lemma says it follows that for any delta, if let's say phi inside is a maximal delta discrete set in m prime when I shrink it by tau by epsilon over 2 plus delta, so phi prime is phi prime is set, and let's call it phi is the set of v delta balls center at phi prime. Then phi covers m the shrinking of phi prime by epsilon. So you have let's do it. This is m prime, and you look at the epsilon over 2. This is m prime shrinking by epsilon over 2, and then you shrink it further by another delta. You know the distance here from any point here to here is at least b, at most b delta. So if you take a maximal delta discrete set here, so the delta balls around them will cover the smaller shrinkage. But if I take another b delta, it will cover up to here. If I take larger ball, they will cover up to here. Okay? So this is what it says. So this is what we will use. We'll use a good cover with centers from delta discrete sets here, and the balls are b of size b plus 1 delta. So actually I want, sorry, b plus 1 delta. Yeah, I should do that. Because the first delta will be to cover the smaller set, and then another b delta to cover the sigma. Is it okay? Okay. Still okay. Now something completely obvious. So let's write it as step 2. Given a convex set, so for any x inside of this xi, which is actually the boundary of the xi, that's another 2. So xi in plane. So x in the xi, that's another 2. But I want x to be in the boundary. This. The epsilon over 2 ball that contain x that contain x on its boundary sphere and lays and whose normal, whose exterior normal x is the exterior normal to this. The same exterior normal is the same with the normal to x I. So this ball lays inside xi epsilon. So it's completely obvious, but it's to be said. So I have the set xi. It's some convex set. So this is xi. And I look at the epsilon over 2 neighborhood. This is xi inflated by epsilon over 2. And then I have a point x here. And I look at the ball of radius epsilon over 2, which tangent. The ball of radius epsilon over 2.
X.
I wanted the ball of radius epsilon over 2. Actually, yeah, okay. So the idea is you look at the idea is this you look at the projection to xi of x. And you look at the epsilon over 2 ball around it. And it's exactly the ball that you want. Okay, so the picture actually proves what said here. And it's completely obvious, but it's needed to be said. Okay. Now another way. Before I tell you what is delta, I will tell you what is d. Constant d. So okay, so what is d? So first, look at the I already told you that I'm going to look at the delta discrete set and we'll cover with ball of radius b plus 1 delta. And then you know, suppose you know you do that, so we remember we have a simplicial complex, and what's the number of neighbors to a given vertex? I need to count how many ball intersect. So every 2 vertex that the corresponding ball intersect, it means that they have distance at most b plus 2 delta, 2b plus 2 delta. So okay. So let's write a fact. The function delta goes to the volume of, let's say, to be careful, let's do 2b plus 3. I don't know, just to be careful. The volume of a ball of radius 2b plus 3 delta divided by the volume of the ball of radius delta. So this, and these are balls in S in the symmetric space. Since this function is continuous, for delta bigger than 0, it's pretty obvious, I think. And the limit, and its limit when delta goes to 0 is it has a positive limit and has positive limit as a positive limit when delta goes. So why it has positive limit? So the limit will be exactly, so you know, if we were in an Euclidean space, then this volume ratio is constant, right? It's independent of delta. You look at the volume of ball of radius 2b plus, this would be supposed to be 3. So 2b plus 3 delta divided by ball of radius, it's a constant, right? And in symmetric space, it's not a constant, but it's continuous. But when delta goes to 0, it will go to the same constants as for Euclidean space, the same dimension, because when delta goes to 0, Yeah, it's in any Riemann net. Yeah, okay. So corollary. For let's say delta smaller than 1, this function is bounded I needed actually here I needed delta over 2. So for delta smaller than 1, this function is bounded by some constant. Bounded by some constant. And this constant I will call d. And you should see why. So this will be the degree of the simplification because I still don't know what is the delta I'm going to use, but I will use some delta which is less than 1, and for all this delta, this d will be. How much time do I have?
40 minutes.
40 minutes. Okay, so I told you what is delta. I told you what is d. Now I should tell you. Now we should choose delta. Okay. So now we should choose delta. Then you will see that so this was step 3, I think. This I should call step 3, this part, maybe. Step 3. And now step 4 is determining delta. Defining delta. Okay, so given a set of points, given y1 up to yd inside S, which are not necessarily distinct, let sigma y1 up to yd be the Chebyshev center or the circumcenter. The circumcenter. So you remember what is the circumcenter? So there is a unique. So it's the center of the minimal ball contained. So in every cut zero space or from convex space, yeah. For non-relatively curved manifold, it's well defined. There's a unique point such that the ball of minimal radius around it contained. So this is a circumcenter. In functional analysis, it's called Chebyshev center. I think in geometric group theory, it's something called Tit center. But anyhow, so let's call it the circumcenter. And here's the lemma. Lemma. For every x in S, any epsilon over 2 balls C, which containing sphere such that the boundary of C contains X, and any D point y1 up to yd, which belongs to the ball of radius b plus 1 on delta around x, but not belongs to the delta neighborhood of C. So, okay, I should start by there exists delta. There exists delta such that for every x, delta is small enough. The inner product then, of the external normal vector normal unit vector of C x with the tangent at x to the segment x carries the center of y1 to yd is positive. And this here. And delta, of course, I want it to be positive and smaller than epsilon over 2b. I want everything to be smaller than epsilon, so exists delta, and I would like delta to be positive and less than epsilon over 2b plus 1. And the point is the following. So you have a point x. Now you have some ball C, I call this ball C, and this is the ball of radius epsilon over 2, which support x. And now I look at the delta neighborhood of this ball. And so this is the same ball that I know is here. I look at the delta neighborhood of this ball, and I will take points, many points y1 up to yd, which are outside this ball. Maybe they're all here. Some set of point y1 up to yd. Twice. Okay, maybe they're all this side. If they are, and then I'm going to look at the circumcenter, and this segment, the direction to the circumcenter, versus the direction of the normal vector, and I want to say that they are correlated. In this picture, it doesn't look like it happens. But you see, if I take delta much smaller, it will happen. Because, okay, suppose we take delta much smaller. And you remember these points were of distance b delta, with 1. So if delta much smaller, this will be hard to draw. So let me draw epsilon large. So this is C. Right? C is the, and this is x. And you see, the center is somewhere there, it's distance epsilon over 2, but epsilon is so large, so you don't see the center. And then you look at the delta neighborhood. This is the delta neighborhood. And then you take these points. So these points are not so far, and the distance distance b plus 1 delta. B plus 1 delta. So suppose they're all here. Maybe they could be separated, but maybe they're all here. Doesn't matter. And then look at this direction versus this direction. Now you see that the positive inner product. And this is, so you see? And this is the proof. I mean, the point is that if you take delta to 0, and now you do the computation, but when you do the computation, you normalize such that delta is 1, and then epsilon goes to infinity because epsilon was a constant, and then this goes to a hyperplane, and you see that the direction must be. So this is actually, is it intuitively clear? So this is very intuitive lamp. So you just, it's believable. Okay. Okay, and now we're finished actually. Well, good. Now we're exactly in the situation. So this determines delta. This will be the delta that we use. And now look what happens. So we have, I already told you what is the cover. I'm using a maximal, so we're basically done, I think. So this tells us that the last condition tells us, so I told you everything. I told you what is the good cover. The good cover is given here. I just told you it modulo delta, but I didn't say what is delta. But now I told you, then I computed D, and then at the end we computed delta. So when you prove that there exists a delta, you assume you already know D also. But it's not, it's actually what you can prove that delta is actually not really depend on D. You see if there are hundreds of points here or 200 of points, doesn't things like that. So, because it looks like a hyperplane. So in fact, every direction to this will be good. Every direction to this. So, but now we know everything. This is the cover. The cover is by balls of this radius, whose centers form a delta discrete set of m of the shrinking of m by epsilon 2 over 2 plus delta. And the last lemma told us that the star contraction to the Chebyshev center, the circumcircle center. So, actually, we have to prove that this is a good cover. We need to show this is a good cover. So we need to show that. So, i.e., for any y1 up to yd which are centers, we want to show such that the balls of radius around y1 of radius b plus 1 delta, this ball up to intersection with the ball. These are the radiuses that I'm using. Non-empty. We need to show that this is contractible. But the star construction to the circumcenter of y1 up to yd, some of them could be the same. It could be that all of them, y1 is equal y2, I don't care. So it's most d point. Just D was chosen. It's a contraction. Shows that intersection. be yi. And goes what to this is contracted. Okay, that's finished. Okay, so we're fine. We have so we show that this is a good cover of M prime, the shrinking of M prime by epsilon over 2, but we assume that the shrinking is homotopic to M prime, and so this is a simplicial complex. So this finished. So now we have all the, now we are ready to the theory. So,
So sorry, the lemma that the inner product is positive and so on
yeah.
will guarantee what that the star
Yeah,
contraction is
This
stays
will
inside the.
yeah, this will guarantee that the starch contraction will stay inside M, inside the shrinking. So you yes, it's guaranteed. So yeah, because okay, let's do it. Let's explain. Yes, let's explain. It's a bit confusing. So there is M prime, something whose complement is a union of complex sets. Complement of X. And I look at the epsilon over 2 shrinking. So let's epsilon over 2 shrinking will be yellow. It is M prime, epsilon over 2 shrinking, and this is what we want to cover. And then I look at the delta shrinking of the shrinking. So and then we have this delta discrete set here, and we use ball of radius b plus 1 delta, because this ball will cover up to the yellow. Okay? And now we need to show that whenever we have such ball, many such balls, the intersection contracts. So if you look at a smaller scale, at a larger scale, so we want to show that say this ball and this ball, we want to show that this intersection is contractible. So what we do is that we take any point on the yellow boundary, take a point on the yellow boundary and call it X. So this is the yellow boundary, and we take a point, and here we have this. This is in the large scale. So, and here we have these two balls. We have this ball and the other ball, and we want to show that this set is contractible. So we take a point here and we call it X. And now we know that here we can draw the epsilon over 2, which is very large, epsilon over 2 balls, and it will be contained in the yellow part. And we have this, and the Chebyshev center of these two will be, okay, in the picture it looks too good, but this is the Chebyshev center, this will be y1 and y2, that's the center, and this will be the Chebyshev center, and so we remember we proved that inside the yellow thing there is a epsilon over 2 ball. And then the delta neighborhood, okay, delta is much smaller. I drew it, because I drew it large, think that it looks stupid. So okay, the yellow is like this, and then delta is still small. But here we have the point x, and here we have this epsilon over 2 port, which is quite over 2. And now we have this point y1, y2, suppose they're here, and or maybe more y3, and the balls, the intersection of the corresponding balls. And here somewhere there is a Chebyshев center. And this direction is the direction that it goes, and it goes out of the arrow because of the data product. Yeah, that's kind of this. Okay, so next we want to apply and to prove so the next thing I want to do is to prove the theorem about non-uniform lattices. So the theorem about uniform, let me just recall what is the theorem. So in order to prove it, I need this lemma on the board, and I need lemma 3.2, which is how to do the deformational term. So tomorrow I'll write. But let me just now write the theorem. So the given S, there are alpha D such that every non-uniform arithmetic lattice arithmetic manifold S manifold is homotopic to D alpha volume M and we're going to do this, but let me just refresh your mind. So recall what we proved in this case. So we had this arithmetic Margulis lemma. I'm reminding you, the Margulis lemma, following, let's call it lemma there exists epsilon and m such that for any such as if gamma G is a non-uniform arithmetic lattice, then for every x in S, the group gamma x epsilon, should I redefine what it is? You remember, it's a group generated by elements whose displacement at x is equal to epsilon, contains a subgroup of index M, which, so a subgroup, call it N x epsilon of index M, which is contained in a connected unipotent group, let's call it by name, U, X, epsilon. So this is a connected subgroup of G. So this is the lemma that we proved. And then I said, suppose further, that gamma is a net. So remember, a net means that every eigenvalue of every, there are no eigenvalues which are root of unity. So if you're in a net, and if you are virtually unipotent, then you are unipotent. Then okay. Then suppose every virtually unipotent in gamma is unipotent. Okay. And then I said something fast, so let me just repeat it. So let's what is a unipotent? So a unipotent, so G is unipotent. We assume that G is linear algebraic group. So if G minus identity is nilpotent. So what does mean? Nilpotent means that some power of it is trivial. But then it means that okay, so if X inside the Lie algebra of G is nilpotent, then X is unipotent. But what is X? X is the sum of X to the I over I factorial, X to the N over N factorial, where N goes from 0 to the dimension of G. You don't need, it's a polynomial, so it's, let's say N, for some finite N. So this, call it G, is unipotent. Vice versa, X, which is defined by the logarithm of G, which is, if you want, the sum N goes from 0 to N of 1 minus G to the power N divided by N, it's a polynomial map, is important. So what I want to say is that for unipotent and nilpotent, the exponential and the logarithm are just polynomial, and so the polynomial, and they're defined everywhere on unipotent group or nilpotent Lie algebra, and there are polynomial diffeomorphism. And you see that for any unipotent, for any G, I mean, we can write G as X, every G is contained in a one parameter algebraic group. What is the algebraic group? You can write it as okay, X of Tx, T inside R. So this is a one, and this group, let's call it also the group generated by G, there is closure. It's the same. It's algebraically closed because the Zariski topology on the Lie algebra and on the group of unipotent group is exactly the same because they're algebraically isomorphic by this polynomial. So you see that and you see that that for any power, for every I, G to the I Zariski closure is the same group exactly. It's the same as G Zariski closure. So if you want the group, if you write here, if you replace G by G to the I, you just need to replace X by IX. And it doesn't change anything. So there is a one parameter group which is well defined and contain X and contain G, and it's the same group if you replace G by a power of it. So what I want to say, and every unipotent group which contains X and connected, it's also contained this one parameter. And the conclusion is that if gamma is a net in the previous lemma, then you don't need to go to finite index. If gamma is a net, then gamma x epsilon itself is already contained in a connected unipotent group. Why? Because since if you have gamma in this, suppose you have gamma in this, suppose gamma is in gamma x epsilon, then gamma to some power, I don't know, m or m factorial, is contained in gamma to some power n for n and most n, gamma to the n will be inside this u x epsilon. So gamma to the n is unipotent. Hence, gamma to the n is unipotent. But since it's a net, this implies that gamma is unipotent. But since this is connected unipotent group, this implies that gamma is already there. That's it. So the conclusion is that if gamma is a net, so okay, this is what is written here. But another fact that we said is the following lemma that we proved. And then I'm going to conclude that there exists a constant, don't know what we use, k, depend on g, such that every non-uniform arithmetic lattice is gamma g, admits a net subgroup of index equals k. And this was just a reminder because I felt that I did this. Okay, I felt that this I proved with details, but then this other things about nets I did a bit fast, so I want to explain because tomorrow we are going to use it, and tomorrow we will prove this modulo this and the lemma 3.2 and Yes, perfect.
What is actual?
Virtually important means that a power, some finite power of it is important. So you were not here, but a net in Raghunathan's book, he defines a net to be a group that, or a right number is or a matrix is a net if the group, the real multiplicative group generated by its eigenvalues does not contain a root of root. And then it says that a group is a net if every element. And then it proves that every finitely generated group admits a finitely subgroup, which is a net, which is a strong, very useful version of what is known as Hilbert's plan. So in particular, you see that, let me just say one remark, we will prove this theorem for S manifolds. But you see that for non-uniform arithmetic, in this statement, you don't even need them to be torsion free. So every non-uniform arithmetic contains a subgroup of index K, which is a net. A net is in particular torsion free. So it's the corresponding orbifold is a manifold. So all these results about homotopy type, number of generator, number of relation, presentation, all these things, in the non-uniform arithmetic case, you don't need to assume that it's torsion free. On the other hand, for uniform, for compact lattices, we will assume this, and I don't know how to avoid it. If you want, for non-uniform, there is a bound on the index that you need to take to pass to a torsion-free net. For uniform, you don't know to bound this index. It's like you can go confirm. And it seems to me a difficult question to deal with this index, but I don't know. Okay, so yes, so the plan is tomorrow to do this, and this will not take the whole lecture. This will, well, completely ready. It will take the first half an hour, I think, and then tomorrow I will describe the rank 1 case in more detail. So I'll come back to the fixed in decomposition and describe the geometry, and then I'll also describe what's happening in three-dimensional manifolds. So we have a weaker stage there. The advantage of doing the rank 1 separately is that in high rank everything is arithmetic. And once we finish with the non-uniform case, when we deal with the higher rank later, we can soon go in a compact case. And this will be another advantage we can do in a different way. Okay, so thank you.
Okay, just one announcement. So tomorrow's lecture with Rashid is at 1:30, between 1:30 and 3. Yeah, I think an email will circulate, but all of you are here.
The morning lecture is there?
Morning is not there yet. Only one lecture between from 1:30 to 3.
And the colloquium is?
And the colloquium talk at 3:30. This half an hour gap. Colloquium talk at 3:30.
No, there is only one lecture tomorrow.
Aprameyan. I circulate the
Was
email
supposed
also.
to be
Yeah,
two
maybe
today
these
and
people are not
by
in
me.
the
that's put on the
Yes.
notice board.
So it's not there on the notice board.
Near the
But all of you are using anyway already.
Yeah.
This room has been a bit.
Yeah, since you have them.
Yeah, I have it ready. So
I was
So it's 1:30. There's no morning lecture, yeah. But anyway, you can all come here for lunch and then.
Yeah.